Morning, everybody. This morning we have Jim Drake as our morning speaker. So, and here we go.
That was an introduction.
Well, I could go on. He just got the Maxwell Prize.
Tell us about Jim.
Jim is a wonderful guy who's highly awarded.
I don't know about the last one, but okay. So what I'm going to talk about is the development of turbulence in 3D reconnection. I'm not going to talk about island formation like Bill Doughton was talking about. I'm looking at finer scale turbulence, high frequency stuff. And particularly going back to the 50-year-old topic of anomalous resistivity and what role it might play. And what I'm going to show you is some recent results which are new enough that I don't really have a full set of movies and stuff to show you, but I have a few things. It seems as if anomalous resistivity is really not the dominant process, but I'm going to argue, in fact, that the dominant process is, in fact, effectively an anomalous viscosity. And so the main authors are Hai-Hong Che, who's a former student who's now at the University of Colorado, and Mark Swistak. Okay, so during collisionless, I'm going to argue first that collisionless reconnection is ubiquitous, and that may not correspond to the stuff that Dimitri talks about in where apparently collisional reconnection dominates. But in any case, and the result of that is that, and why I say that is because reconnection electric fields typically exceed the Dreiser runaway field, and that's even true in the corona, which is nominally modestly collisional. If you look at late time and you estimate fluxes, magnetic fluxes and time scales over which they reconnect, you can put in the numbers, and typically you exceed the Dreiser field by quite a bit. And once you exceed the Dreiser field, it's very hard for classical collisions and the resultant resistivity to be important. And certainly in the magnetopause, magnetotail, and the solar corona. And during Sawtooth and tokamaks, it also seems to be the same case. You can calculate the inductive fields, and they typically exceed the Dreiser field. So in the absence of classical dissipation, then the question is, what breaks magnetic field lines in collisionless reconnection? Now, in the last few years, there's been a fairly broad consensus that the electron momentum transport associated with thermal motion actually breaks field lines. And this is, people always talk about the so-called off-diagonal pressure tensor, but that represents exactly what I said. It gives you effective momentum transport associated with the thermal motion of the particles. So that often seems to work. On the other hand, historically, anomalous resistivity has often been invoked. And the idea is that when you have reconnection near the X line, you get these very intense current layers. And that streaming could drive turbulence, which produces enhanced electron-ion drag. And it's certainly true that observations, if you look at the observations and you compare them with the simulations, the observations are a heck of a lot noisier than what we see in the two-dimensional simulations especially. And there's a lot of turbulence. Electron plasma waves, lower hybrid waves, Whistler waves, electron holes. But one of the challenges is that in spite of the fact that they see all this turbulence, their role in breaking field lines or not has never been established. It's not an easy problem. You see a bunch of waves, how do you tell what those waves are actually doing, especially if you wanted to argue that they're breaking field lines? It's very hard to establish this, and some of the arguments that people have gone through are extraordinarily crude. So anyhow, the role of all this stuff, or what it's actually doing or not doing, is really up in the air. So what has been seen in the last number of years is, for example, electron holes. And so here's an example from a magnetopause crossing. Here's the the magnetic field reversing component, reversing direction. Well, wait a minute, what is this? Okay. Here it looks like the magnetic field reversing. Let's see, where's the pressure here? Is this the density? I can't even read it.
Yeah, well, that's spacecraft potential.
Yeah. Oh, so this is the effective a measure of the density.
Yeah.
So I think we're going across the magnetopause. So it looks like the density is low and then goes up higher. I can't hardly see in this plot, but it's higher at the end. So I assume we're going from the magnetosphere into the magneto sheath. Does that look right?
Yes.
Yes. Okay. Okay. Anyhow, the field, the vertical component of the magnetic field at the magnetopause then reverses sign. And you see this burst of wave activity. And if you blow up one of these periods, looking at the electric field, you see stuff like this. And these bipolar signatures are called electron holes. And so these have now been seen really throughout the magnetosphere, both in the magnetopause and in the magnetotail. And so these structures are pretty large electric fields, and I think we believe that these are associated with separatrix crossings, where you have reconnection going on. You cross the separatrix, and you see these structures whizzing by you at high velocity. But especially since typically you see these along separatrices, it's not clear that they play any role at all in the reconnection process. Okay, so here's a more recent observation from Jonathan. Oops, sorry.
Not that.
You can tell I put these slides together yesterday and today. There's another Eastman, but so I somehow got screwed up here. Jonathan Eastwood, 2009. This is a PRL. And this was from cluster observations in the magnetotail. And so here you are. And you see, this is in a local coordinate system, a minimum variance coordinate system. So BL is a reverse field. You can see it's nicely reversing. And the claim is that this, the cluster went through the ion diffusion region. And I guess this is the frequency spectrum of the turbulence that they're seeing. And so what they did was they analyzed the turbulence during a period before and during the crossing.
The top panel is actually particle.
Oh, this is the particle data? So there's no turbulence in this.
Spectrum, but if you look
Okay.
at 1, 2,
Yeah, so I'm going to show the spectrum here. Okay, so this is the particle data. I couldn't quite. Oh, this is an EV or something? Yeah, okay. So here's the spectrum prior to entering into this region. And then here's the spectrum after. And you can see the electric field spectrum and the magnetic. So here's the electric field spectrum, and here's the magnetic spectrum. So it jumps up by a couple of orders of magnitude.
Now, since we've been arguing about it, when you say Whistler-like, are you happy if we call it kinetic Alfvén wave-like?
So Jonathan, what do you have to say?
Well, it's kind of tricky because it's such a small region to do any sort of statistical analysis to really say what it is. And what I've done is, so the red line is the electric field, the black is the magnetic field fluctuations. And you can do some analysis to estimate a propagation direction and then turn it over into dispersion relation, which is in the middle. And so roughly it fits with It fits better with whistle waves than anything else, but it could be kinetic alpha. There's no guide field here in this reconnection, so that's playing a role too.
Now the omega over omega, is that omega pi?
Yeah.
Pi or ci? I mean, the large omega. Sorry, the y-axis of the middle plot.
That's omega pi, the ion.
Oh, okay.
Do you know how omega compares to omega CI?
So it's cyclical or plasma?
Yeah, it's a cycle. Yeah, is it
That's cyclical.
That one's
cyclotron?
cyclotron. Oh, okay, all right. So the question is that the plasma frame or the satellite frame frequency?
That's plasma frame. It's all in the frame.
Okay. And what are, it's really hard to see the left side of 10 to the 0, 10 to the minus 1.
10 to the minus 2, 10 to the minus 1, 10 to the 0, 10 to the 1.
But since it's the tail, right, then frequency spectrum isn't exactly the case.
Not here, but
Is that
this is with the, so this was from cluster where with the four spacecraft you converted all from frequency into space.
oh, so this is
So in the middle panel,
Mm-hmm.
it really, what I tried to do was really it's really k as, or omega as a function of k, and get it as close to theoretical as
Yeah, all right. Whistler it is.
But this is just one example, right? There are other diffusion regions where the evidence is kinetic alpha anyway. So,
Yeah.
you mean you have those black dots that follow the green line?
well,
In other cases.
in other people have published evidence. I'll talk about it more on Friday.
Oh, have you seen cases where it actually rolls over down? Huh? Yeah.
There's a paper by Chris Chaston, PRL, 2009, in a different event with a guide field where he saw kinetic alpha waves as well. It's an open question.
But you have to be careful when you say guide field because, you know, you're talking about perturbations here, and I think as soon as you're away from the X line, you have a finite magnetic field, and so then whether you say you have a guide field or not, I think it's not clear. Yeah. Especially for the, you know, unless you're in the electron diffusion region or something like that. Okay, now he has this quote in here. The associated anomalous resistivity was not found to significantly modify the reconnection rate. Now, how in the world you made that statement, I have no idea.
This is not a presentation of questioning the view.
Well, it's part of the issue here. You know,
That's why we travel, so we can talk.
if I was the referee, I would have called you on this one because, you know, this is a tricky business to say that. Don't you think? I'm really putting him on the spot. Yeah, it's a pretty tough statement.
My wife used to work in a law firm, and one of the rules was that you get to see what the other side is going to say before you.
Okay, sorry. I'm just quoting a published result.
So that's right, that's what she's doing, so you better
No.
Okay, anyhow, I just did that for a joke. Okay, so let's remind ourselves what, oh my gosh, see these things, they never come out right in here.
We're used to it.
Isn't there any way of brightening this projector? It's not adjusting the,
maybe that will increase the light.
yeah, but, yeah, okay. Okay, so anyhow, this is just to remind you, if you do 2D guide field reconnection, sort of what you see, and so I think this is similar to what Bill showed. So here's the out-of-plane current, and here's the classical sort of tilted. You can see this is a modest size simulation. These are in dP means the proton skin depth. So you see the classical tilted current layer, and notice these interesting little vortices that are developing here. And these tend to seed islands periodically. And then this is the ion outflow velocity to the left and to the left and to the right. And don't worry about this one. This just to show these density cavities that we've been discussing earlier. And so, so the white is the cavity. It's pretty low, and then so you compare the, of course, I wouldn't take these too seriously. This is a remnant from the initial current layer. But so what you want to look at is the difference in density between here and here, which is fairly substantial.
And also with the upstream density.
Yeah, the upstream density is like, I think for this simulation it was like 0.2.
And the white stuff is it possible to say how?
It's possible to say that it's not 0, but maybe around 0.1 or so. I mean, I can do a cut, but I didn't do it for this talk. If you really want to know how deep the cavity is, we can do a cut. Now, these current layers get really narrow, and I think there was earlier predictions that these things can scale like, from several different authors, that these things can scale like rho e. So for a strong guide field, then they can be really very, very narrow. This one was done for a guide field of 2 compared to the reconnecting field. So all these normalizations, when I say the guide field is 2, then I'm comparing always with the reconnecting field.
So, are there electron holes here?
That's more in 3D.
No, you can see electron holes. You even get them in 2D because the guide field, when the parallel streaming of electrons is along the magnetic field, and there's an in-plane component, and in a big simulation, that's typically sufficient to drive electron holes. So typically you see so if I plotted the electric field in one of these things, you would see electron holes all the way down the separatrices. And typically they're larger actually down here in the cavities. Okay, so now let's get down to talk about how you break field lines. And to discuss that, you need to talk about the Ohm's law. So the Ohm's law basically starts from the electron momentum equation. So here's the z component, namely the out-of-plane component. So my coordinate system will be the same throughout. It's x horizontal, y vertical, and z out of the plane. Okay, so the out-of-plane component of the momentum equation in conservative form looks like this. So this is the full pressure tensor, V cross B electric field, and the convection of electrons. And then if you have turbulence in the out-of-plane direction, it's useful to average over that turbulence in the z direction because that eliminates a lot of big terms. In particular, the pressure term has some large terms in the out-of-plane direction, which you would like to get rid of. And so you average this thing over z, and you get something that looks like this. And so, okay, so here's EZ just from this, and the V cross B. Here's the pressure tensor, and the inertia term, electron inertia term, and here's the convection terms. And there's 2 additional terms which are important that are associated with the turbulence. So all these exist at finite values for the 2D case. These are the things that arise from turbulence, and there's 2 of them. The first is the so-called drag term, and that comes from correlations between the density perturbation here and the electric field perturbations here. So this is the classical drag term that gives you anomalous resistivity.
Why do you average over z? Is it equivalent to averaging over time?
Yeah, this is like an ensemble average. We're trying to mock up an ensemble average or a time average. So you're not interested in the phase dependence of all the turbulence, so you need to have some sort of averaging procedure. So procedurally in the particle simulations, we do a z average.
Oh, okay. So for practical.
Yeah, I mean, one in principle could do a time average, but it's tough because that means you have to print out an enormous amount of data.
Yeah.
It's difficult. Okay, so So of course, what this also means is if you're analyzing spacecraft data and you really want to talk about anomalous resistivity, you're really supposed to do this correlation. Because anything else involves theoretical models, and of course everybody here knows, since you're so involved with the turbulence problem, that the phase correlation between these things makes a big difference. And so invoking some theoretical model, because you don't really know this, but you know that, is really very problematic. So actually measuring this correlation is something which is very important and as far as I know has never been done.
Which way is Z?
This is the out of plane direction. Yeah.
But it's never been done because they didn't care, because there is technically not possible.
Well, I think measuring delta NE is difficult, although I don't know whether the spacecraft potential might potentially be able to do this.
It's difficult on the scales in which you want to do it.
Yeah,
Yeah.
right. Do people look at the noise or the turbulence on the potential analyzer?
Well, I mean, to put it in context, we have, well, like I'll say, we only have of the order of 20 diffusion regions to look at. And so we're still, I think experimentally, people will be more like actually identifying them. And so looking at this is still on the cutting edge.
And you
Yeah.
have to get lucky when you fly long enough along the guide field to get an average.
Well, the turbulence is streaming by pretty fast, and so the spacecraft, for all practical purposes, is stationary. So you see all this stuff barreling by you. So in principle,
Spacecraft elements will just is it streaming by? I mean, when you're in the momentum table, right, it's not streaming by very much, is it?
well, if we're talking about a instability driven by an electron intense current layer, and those electrons have high velocity, and certainly they're moving much, much faster than the spacecraft is. So it comes sweeping. It's like, for example, electron holes. They come blasting by you at very high velocity.
So this is why you see many of them, even though you're crossing the separate.
Yes.
And they're all aligned on the separate.
Yeah, they're aligned and they just,
Yeah.
yeah.
Will MMS be able to measure the density and
No.
cadence?
MMS is, they're going to try to measure the density on some time scale, but keep in mind that we're talking about high-speed flows of short wavelength turbulence, and it's coming by you. There's just no way in the world you're going to measure the distribution function.
No, but just the density, overall density.
I don't know. Maybe Jonathan but I really doubt it. But
I think you could construct some measurement like this even with existing data.
maybe if you just looked at one direction.
But I don't quite I thought your simulation was 2.5 feet, so there's no variation in set.
No, I gave that as an introduction. The first plot was an introduction.
But your stuff will.
I'm
Oh,
going
this
to,
is not single, this is just.
this is a theoretical analysis.
Okay, I'm
Yeah.
sorry.
But we're going to evaluate all this stuff from the simulation. Okay, now, so here's the conventional term, and now if you go back and look up here, you realize that there could be turbulence in the electron flows and everything else, and there will be a momentum perturbation transverse to the z direction correlated with a momentum perturbation along z, and that produces an effective viscosity, and that's this term here. And so the first piece comes from here, and then there's a magnetic perturbation piece from here, which combines nicely so that this is the canonical momentum. So you get a correlation between the transverse perturbation of the electron flow and the electron canonical momentum.
Jim, what are you doing about the tensor PEC? What do you assume for a form of it?
I'm leaving that. That's here, it's still there.
Right.
So you just average over z.
It's actually how do isn't it tricky to separate the pressure tensor from that presumably.
This is the traditional separation where you just define at any given location a mean velocity,
Right,
subtract that from the pressure tensor.
Right, which means that to find the mean velocity, you do some ensemble averaging locally at the moment of time.
No, that's just a local average over velocity space.
Right. But that's particular velocity.
Yeah.
So he's not doing anything that's. No, I understand. But I mean, when you then separate turbulent random velocities from thermal random velocities.
Yeah, but I don't do that. This is all traditional with the standard definition.
No, I understand.
And yeah, right.
But in practice,
So the canonical term only comes in if you have 3D simulation?
No, I mean generally speaking, this will be there.
Like if you have 2D, isn't the canonical momentum conserved?
Yeah, right.
So then it wouldn't fluctuate, right?
Yeah, so so I'm going to show you 3D simulations when I'm evaluating this. This term and this term sort of nominally go to 0 in 2D.
Which term goes to 0?
These are the turbulence terms. Now, it is true in two-dimensional system you do get some turbulence, but that would be in plane direction, and I'm not talking about that.
well, I was just worried about this. So you have the velocity that enters here is the fluid velocity.
It's the fluid velocity.
Which you obtain after you average over the particle distribution function with extracted mean
Yes,
velocity.
right.
And yet that fluctuates rapidly. So I mean you have to.
You're worried about this intermeshing the
Thermal average.
yeah, right,
versus thermal
right,
average,
yeah.
whether it's not-
But in practice, the main point is,
Normally, yes.
yeah. I mean, in our code, we can just do this because we have the full distribution of particles, so you can average over velocity and you get a mean velocity, and so practically speaking, this is doable.
Have enough particles.
Yeah, we have enough particles.
But in your introduction 3 slides ago or so, you said that you were worried about the thermal off-diagonal momentum business.
That's this one here.
Yeah, so since that was in the introduction, I've been staring at that term waiting for you to talk about it.
I'm going to talk
These
about it.
D's and T's, do we really care?
Yeah, okay, that's the question.
Okay.
Okay, so first of all, let's collapse to 2D now, okay? And let's look right at the x line. So in 2D, this stuff goes away, and if you're interested in steady state, the inertia term goes away. The velocities go to 0 at the x line. So all this stuff goes away. That's gone. This goes to 0 because B goes to 0 at the x line. And you're left with this must balance that. And so that's what I would call thermal momentum transport. And it's been well verified in the typical simulation, 2D typical simulations in steady state, that in fact these two do balance. Okay, now the question, of course, we kept asking, so, I think many people, with the exception of us perhaps, said, okay, this problem is solved. We have this balancing this, and that's the end of the story. But on the other hand, there's all these observations of turbulence. And furthermore, you have to ask the theoretical question, and that is, what happens as you let the beta of the plasma get lower and lower and lower, so that the thermal speed starts becoming very, very small? Is it really true that this thing can continue to somehow balance?
The only way to do it is if you have strong guide field that you have it lower relative to the guide field.
Right. So it's very clear that in the anti-parallel reconnection case, this thing is gonna probably always balance that.
Is the beta low because the density is low?
No, I wouldn't say that.
But then we'll just divide it back up again.
Because what?
If you just lower beta by decreasing n, like then.
No, I just let T go to, I'm talking about letting the temperature go to 0. I mean, the density drops out, so it's not, it's really the temperature. Yeah. And of course, it's the temperature which gives you the transport, because the electrons, if they're moving around a lot, they can carry momentum away from the x line. So, I mean, this makes perfect sense. But as that electron velocity becomes small, then you really have to ask the question whether that can occur. And yeah.
Do you think is it the total data you think that's important?
No, just the, I think it's the one?
Is it the data based on the reconnecting field or the data based on the total field, do you think?
It's probably associated with the total field, but this is still uncertain. Yeah, I think because the guide field constrains the particle electron motion and inhibits the electron flow out. So I think the guide field plays a role in this. Okay, so to address whether this thing ever fails, we started looking at high guide field, low beta E, the electron beta, to try to see whether this continues to hold or whether it breaks down. Okay, so let's see, what am I saying here? Okay, so what we're talking about here is turbulence, whether it produces anomalous resistivity, anomalous viscosity. And so, of course, there might be pressure gradients could drive turbulence too, so-called lower hybrid drift instability. And you don't see this stuff, well, you do see some of it, but not so much in 2D models because it's harder to align the wave number along the current in 2D because the primary current is out of the plane. So again, in antiparallel fields, I think the turbulence seems to play a minor role, although Bill's doing the simulations of MRX, which may reveal some turbulence, because MRX does see some turbulence, and I don't know why. Oh yeah, let me make a couple of other comments. There is some circumstantial evidence that turbulence might be playing a role in some cases. One is in MRX, in which the electron current layer is wider than simulations typically predict. And so Bill has been simulating this, and what's the factor?
Like a factor of 3 to 5.
Okay. And then there's a very nice case that we published with Typhon for a magnetosheath in which they've got a nice measurement of the electron current layer. And the parallel simulation we did of that is also off by a factor of maybe 4 or 5 in terms of the electron current layer is clearly wider than what we get out of the simulations. So that's circumstantial evidence also that something's happening. Okay, so we're focusing on reconnection with a guide field in the low beta E case. And of course you can get islands growing on other surfaces, and I'm not going to discuss that. And then the electron streaming velocity gives you Bunemann instabilities. We see lower hybrid instabilities, not lower hybrid drift, but current-driven lower hybrid instabilities. And you see this strong nonlinear state with these electron holes. We always see both the lower hybrid instability and Bunemann produce these nonlinear structures, electron holes. And you get modest anomalous resistivity. But it doesn't seem to stop the electron runaway. And the problem is that imagine you've got a distribution of electrons going to high velocity. In order to stop those, you have to be able to resonate with every single electron. In other words, you can't just resonate with the lower tail of those electrons. You've got to resonate with every single electron, otherwise some of them are going to run away. And that seems to be the difficulty. We see the electrons, some of them get dragged back and you get strong heating, but there's always this tail of particles which seems to keep going to higher and higher velocity. So it never really totally seems to work.
But why is it bad?
Why what?
Well, you don't want to have some particles going to higher energies. You want to have particle acceleration.
The problem is there's enough of them so they have substantial current.
Okay.
And then so the current layer gets narrower and narrower. You get this very narrow, intense current layer.
And it's all carried by runaways.
Well, yeah, it's carried by runaways. Well, all the particles in principle in these simulations are runaways. But there's some particles get dragged back, but there's a substantial chunk that just sort of keep going out. Okay, so what we see, in fact, so what I'm going to show you is that the the current layer keeps narrowing until you get this instability, which seems to be driven by the current gradient rather than the current itself. And that completely breaks up the electron current layer. It becomes a filamentary layer. And then you can calculate the anomalous viscosity, effective anomalous viscosity. And this, in fact, balances the reconnection electric field. And the pressure tensor term never gets big enough to do anything. It stays small. You might guess it could have heated up the electron sufficient so that the pressure tensor term plays a role, but it doesn't seem to. Okay, so here's well, that yeah, so that was right. But the way we're doing it, we're separating that effect in putting that into flows so we can calculate it. Okay, so the simulation I'm going to show you is relatively small, but it's 4 by 2 di by 8. And you notice it's much longer in the out-of-plane direction. That's because it's hard to get enough statistics. You've got to have statistics to start analyzing Ohm's law. And so we keep increasing the out-of-plane direction so you can get more and more statistics so you can do a good analysis of Ohm's law. And in the process of doing that, we got the unexpected, which was this new electromagnetic instability, the shear flow instability, which we first saw with this box. We never saw it for a shorter box. Okay, so this is the reconnection rate versus time. This is in ion time units. This is the 2D case here, and the 3D case comes up, and then suddenly it jumps up by 30% or so when the turbulence really onsets. And this is the width, the half width of the electron current layer. This is normalized to ion skin depth. And you can see it keeps going down. In the 2D case, it keeps going down and down. And then suddenly in the 3D case, it jumps up. This is associated with this onset of this electromagnetic instability.
So that's 0.2, is that in
C over omega pi's. Okay, so so at late time, here's the X line. The magnetic field reconnected. You can see this is the paraelectric field. And it's in this density cavity. There's a density cavity which is running along this direction. And here's the out-of-plane current. The out-of-plane current runs along the other direction. And you can see it's noisy looking. And here are the momentum transport terms, this TEZ that I showed you. And here's the drag term. And the momentum transport term, and all these are normalized in the same units, namely the electric field unit. So when you look at the reconnection electric field, which is basically this, it's like, 0.1 or so. And the momentum transport term is of the same order. And the drag term is smaller. And furthermore, the drag term spatially is different from the momentum transport term. In fact, the drag term isn't even peaked along the current layer. So you can see the drag term this is not anomalous resistivity, even though we're talking about drag. It's not anomalous resistivity because it simply doesn't even peak where the current is the largest. It peaks in the region where you have a paraelectric field, but it doesn't even peak in the region where you have the dominant current.
Because it's killed off the current?
No, that's not it. It's because in this density cavity, it's very low density, so it's high velocity particles that are in there, but there's not enough density to produce any significant current. So if I plotted the electron streaming velocity, you would find that it peaks in this region. But the current itself is not, because there's this big density cavity, so there's hardly any plasma in here, and most of the plasma is along this region here, which is why you see this current dominantly tilted like that.
But it does balance the electric field in this region, right? Where it is.
This one.
No, 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 electric field and D are in the same angle.
Yeah, that's right. That's okay. So along the density.
No, it's too small. This is too small to balance that. Yeah.
But then it went back to high in-plane beta, and the density cavity became small.
What do you mean high in plane beta?
So beta, you go to the beta based upon the Bx is large, but the beta based on Bz, say, is small.
Yeah.
And if, in that case, if delta n over n became small, which I was thinking it might, would that change? You wouldn't get this. The density cavity would then become small. So the argument you just made regarding the velocity of the particles having to become large would.
So why do you think the in-plane beta controls how big the density cavity is?
Was the argument I gave during
Yeah,
my
right,
talk, but
right,
I've
right.
done two fluid simulations, and it seems like that's the case.
Yeah, but the two fluid simulation doesn't really do the density cavity.
Well, we need
Yeah.
to check this out.
Yeah, right.
Obviously.
Yeah.
Do you have an answer to that? What controls the density cavity?
So do you want me
How
to?
does it depend on the gas field?
So I can explain to you why the density cavity forms, but I don't know the scaling of the density cavity.
Okay.
Okay, so the density cavity forms because there's a reconnection electric field that's a parallel electric field, and electrons go streaming. The electrons are accelerated towards the X line by that reconnection electric field. They go zipping around here and are out the other side. And that drains this separatrix. And then it gives you higher density on this side. And that's the reason that the current is so large over there, because you've got so many more particles here than here. And this really does literally drain, the density gets really low in this cavity. From that earlier slide I showed you, you can see that.
Could it be because you have final sort of system size, so there is
No, that's
source
not it.
for this electrons to enter?
How do you drain away the ions though? Like, I think that's.
They move across. So this is a classic kinetic Alfvén wave. This whole thing, it's a kinetic Alfvén process. Kinetic Alfvén wave, you have parallel motion of electrons, and the ions go across the field to charge neutralize. And so in this density cavity here, there's a transverse electric field which is large, and that pulls the ions out of this
Yeah.
cavity.
But why can't electrons move all the way?
Why doesn't it refill? It's periodic.
Right.
Well, yeah, it tries to, but by the time it gets around here, then this field line has already moved in. If you look at the electron parallel flow velocity, you can see electrons spiraling around inside this thing. And of course, the larger the guide field, the longer it takes to do that. These guide fields are pretty, you see these too, Bill, don't you? Yeah. These are very robust, these cavities. Okay, so let's see. I don't want to talk about this stuff yet. I'll re-show this later. Okay, so what I want to show, so here is across the current layer and along. So now we're looking in the out-of-plane direction. And so here's what the current layer looks like. I think this was at a time of 3.0. And so here's an X component of the electric field. And here's structures you can see are localized along the magnetic field. And so all these things are electron holes. So we've seen, a number of people have seen these in the past. So here's what electron holes look like. They're localized structures. If I plotted EZ, you'd see these bipolar things, but I just plotted the other component of the electric field. And the there are some magnetic perturbations here, but look at the scale, 0.02. It's relatively small. Because these are too short a wavelengths, basically. The dominant turbulence is very short wavelength. The electromagnetic component is very small. So here's at 3.5. And it's really very sad that you can't see this. This is after the onset of electromagnetic instability. So first thing you can't see is all this filamentary structure on the current layer. The current layer has basically filamented up, and you see all these beautiful strings of electrons going down here. Here. Maybe you can see better here, but yeah, it's cool. When I first saw this, I was really excited. So, and then you notice the sudden jump in the size of the magnetic perturbations. And the electric field, you see it's jumped to long wavelength. It's really a fundamentally different instability. You've gone from these very short wavelength things here, and now suddenly they're very long wavelength. This is a cut right through the X line, yes. Yes.
Does this develop? Do those density cavities combine, or do the small scale ones fade out and the larger scale ones pick up? I mean,
The
do
larger
you
scale
understand
ones.
dynamically how you go from the bottom plot on the left to the bottom plot on the right?
Those just merge, or is there some new thing merging?
I mean, you can
As far as I know,
imagine
no, it's, well,
poles merging and then
you know, who knows?
an inverse cascade.
You know, you could imagine that this instability acts as a seed for the electromagnetic instability, but, you know, I don't know. Yeah. I suppose we could, yeah, I have a movie of all this, so I suppose I could try to look and see a time sequence of this and see whether some of these things actually merge in to form this,
Yeah.
but I haven't done that. Okay. Okay, again, keep in mind that the axial field is pointing to the right here. So all this is along the field line. So it has a finite K parallel. It's long wavelength along the field. Okay, so here's a movie of this electron current layer. So again, the magnetic field, oh, you can't even see anything here.
Oh, it is running?
No, it's not running yet, but there's a current layer which I can see on my screen. Yeah, I'm going to cut this thing around.
Oh, wow, it's missing.
Okay, hopefully you're going to see something in a minute. So it's shrinking. The current layer is shrinking. Just breaks up. It looks much better on this one. You can tell the electrons, of course, are streaming to the left.
What is rho E in this?
Rho E is very small. Yeah.
Mass
This
ratio
is much,
100.
Rho E is much smaller than any of this
No,
stuff.
this guy.
Yeah.
What is it?
Uh,
Mass ratio 100 you said?
Yeah, this is a mass ratio 100. I don't remember because TE was 0.04, so square root of TE. Yeah, 0.2, so 0.2, and the guide field is 5, so 0.2 over 5, 0.00 something. Yeah. Oh, let's see, did we get the mass ratio in there? It's even smaller than that. It's small. It's small. The current layer never gets to Rho E scales because it breaks up before that.
But the filaments, these individual filaments, are they at rho E scale?
I don't know.
I think they are. Because, I mean, this is a C over omega pi, right?
This is C over omega pi, right?
That's,
I'm going to show you a simulation in a minute which has got only electron scales. Maybe that'll help. We can look at that a little bit more. But, you know, we haven't, studying this turbulence, I mean, we just haven't done it yet. And we've just done some very brief things to try to understand what is it that drives this instability. I mean, there's clearly some very basic questions which we've just started to answer. We certainly have not studied the nature of this turbulence. Okay, so let's see. So here we are back to that earlier slide I showed you. So again, here's the reconnection rate, here's the 3D versus 2D, and then the broadening of the current layer. And this just shows the variance of the three components of the electric field. So this is the parallel EZ component, and I think this is EX and EY, averaged over the whole box versus time. Okay, so let's go to this. This is the Ohm's law terms. Let's see, do I have another slide? So here's the momentum transport term. This is the electron inertia. So keep in mind, at early time, we've got very, very low beta system. The pressure tensor term just can't do the balance. And so the electrons just keep increasing velocity, and that means the inertia term is just balancing the reconnection electric field. Electrons are just running away. And that goes on and on. And here's the anomalous transport terms. So at late time, you get these electron holes, and they produce an anomalous resistivity which you can evaluate. And then suddenly this onset of the electromagnetic instability. And this just completely kicks up and wipes out all the anomalous resistivity basically completely. It goes away. The inertia term drops down to 0 because it really stops the runaway. And the transport term, the momentum transport term at late time balances the reconnection electric field.
Where are these simulations?
This is right at the X line.
So it's just one point of the...
Well, it's a little tiny average around X, or around the X line.
So the X stays in the same place, it doesn't get pushed around there?
Oh, well, it jostles around a little bit, but not much. Yeah.
Answer my question with this slide.
Yeah. What do you want to know?
I was just wondering whether is this like an electron EK electron photon mode or something?
Yeah. I mean, okay. You'll see in a second. Barrett actually worked on something related to this. Okay, so the fact that the current layer broadened suggests it's an electron shear flow instability. And then there's a lot of fundamental questions. What about the role of ions? What about the dependence on the strength of the guide field? So what we decided to do was a series of 3D PIC simulations of a thin electron current sheet, again with a uniform density, so there's no lower Harbor drift type stuff. And we took an initial current layer width of about electron skin depth because that's sort of where we saw the onset in the reconnection simulation. And we've tried various mass ratios and guide field BZ. So we actually started with saying, okay, we put in a mass ratio of 1600. The fact that we're doing this small scale current layer means we can really vary the ion mass ratio up to realistic values. And so we varied the guide field and the mass ratio, and we did it with a mass ratio of 1600. The instability was still there, so we said, okay, shut off the ions. The instability is still there, and this is a guide field of 2.5. So here's the initial current layer, and this is what you get from the 3D simulation. I'm sorry? Yeah, it's DE. Yes, we put in an electron skin depth scale current layer. So now the ions are out of the picture. So there really is a shear flow instability in a kinetic plasma. It's very strong. Okay, so then we tried different guide fields. And now this is plotted as cyclotron frequency times time. And this was a first surprise. So remember, we start our simulation, our reconnection simulation had a guide field of 5. So then we said, okay, 2.5, and it was stronger. Although, interestingly, it doesn't look like the growth. Oh, by the way, this is b wiggle squared, bx wiggle squared averaged over the entire box. 2.5 was strong, although, I mean, if you look at once the thing starts to onset, it really doesn't look very different. And then 1.0. And that's arguably stronger. But 10.5. It goes away with guide field too small. So this was a big surprise. Except for the fact that I'm going to show you a dispersion relation which actually made this prediction, but we just didn't know it.
Do you understand the non-monolith?
No, we don't. This one, we can't figure out why is this going on. I have no idea. We haven't figured that out yet. Okay, so we decided that the simplest model we could think of was the electron MHD equations. And okay, the other thing I didn't tell you is that I analyzed from the data from the reconnection simulation and showed that this is a right-hand polarized wave. So it rotates with the electrons, which is the Whistler sense. So the fact that the ions didn't do anything, didn't seem to do much, and it's an electromagnetic instability. It rotates in the Whistler sense. So we decided we would try the electron MHD equations. And Ferraro and Roger, I have a paper in '94 in which I simulated this type of thing in 3D, and then Barrett has a paper, Ferraro and Rogers in 2004, in which they also looked at this equation. So electron MHD equation, the ions are held fixed, but it's fully electromagnetic because anytime the electrons move, they produce magnetic fields because the ions are not moving. So P is, the electron mass comes in through here. And so we try to do a linear stability analysis of this with some initial current layer.
Here you assume the background field is strong. You get dE squared, but not rho E squared.
Zero temperature.
Zero temperature.
Zero temperature.
Okay.
This is the most simple thing you can think of. And then perturbations. Now, there's a limitation. We do local theory, which may be questionable. So we have, but we have a K along the magnetic field and across. And then we just linearize this thing. So you get some local dispersion relation. Oh, I didn't define gamma. Gamma is gamma minus I kz VEZ with no P. Pk has got K squared put in there. So this is the drive term. You can't, even though there's only electrons here, you can't shift to a frame in which the electrons are not moving. Because after all, they're producing current. The current is a real effect. You can't just shift it away by going to the electron velocity and then going to a frame in which it's simply zero. You have to, it doesn't go away by shifting frames. So this is the Doppler shifted growth rate, but then there's an extra stuff here. So you can't just shift that away because it's producing current.
Because there's a shear in it. It's perpendicular.
There is a shear, but we're not even taking that into account.
No, but I mean,
Yeah.
that's back in the code. That's why you can't get rid of it.
So you have to DJ the wiring.
Yeah, this is dJ dy.
So is that why you can't shift the
Well, I mean, you could imagine just saying, I'm going to go to a frame in which there's shear in the current, but the current is zero. But you can't really do that to analyze this simulation because there is a finite current, and that current is producing a magnetic field. Yeah.
I guess it could, but then you have to properly.
You can't get rid of the magnetic field associated with that current. Yeah. 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 Right. You produce. Yeah, that's right. Exactly. Yeah. Okay. And it turns out this term is responsible for stabilizing at small guide field. Because, well, okay. If you believe this dispersion relation, then this term is the one that's responsible for getting rid of the instability at small guide field, because in the absence of this term, you can see the growth rate scales like omega z squared. But so as this term gets smaller and smaller, where the drive term is, this thing starts to dominate, and that screws everything up so you don't get any instability at weak magnetic field. Okay, so anyhow, you can define a parameter which is basically a dimensionless parameter, which is the derivative of the electron flow speed, cross-field derivative, divided by the cyclotron frequency, and that turns out to be small. And then you can calculate the growth rate. So at short wavelength, given by this, it's linearly proportional to k, and then it goes up to a constant at high k. And it's like a classic Kelvin-Helmholtz instability at high k. You know, the growth rate is just Vz prime. And that's, the Kelvin-Helmholtz has that same behavior. So, yeah.
Density is uniform here?
What?
Density.
Yeah, uniform density. There's no lower Harbor drift or
And
anything.
what is equilibrium, like this current gradient, how they balance in equilibrium?
So the way we do it is to put perturbation in the guide field to balance the variation of the reconnecting field, or the self-generated equilibrium field, Bx. So Bz squared plus Bx squared is a constant. That's what we take for the equilibrium.
This is stabilized at IKZ, right? So that's why you have a long wavelength oscillation.
Yes, right. So typically you find Kz is, depends on where you are because it varies depending on in here, but the dominant stability has Kz much less than Kx. And Kx, C over omega PE is of order 1, and the result is that Kz is smaller. In fact, Kz scales like this small parameter epsilon. So you have long wavelength along the magnetic field and short perpendicular.
So, what is epsilon in this simulation?
It's about a tenth.
A tenth?
Yeah. But you can see how crude this whole thing is. So
I don't know. I mean, you said if we can trust this linear dispersion relation, but why wouldn't you? It's a linear dispersion. You trust it?
not too much. Barrett wrote a paper and he says you can't believe local theory, and
Well, no, some
Yeah.
of the modes, there were some modes predicted by local theory that were not present in the whole theory, but there were some.
yeah. Mhm. I mean, you have to, to justify local theory.
This is what was done back then.
No,
Or is
not
it-
exactly. Actually, I admit that I wrote a paper in '94 in which I wrote a dispersion relation, but it turns out that I screwed up. This term was there, but I had an extra term which turned out, it's one of those things where you do the calculation and it doesn't agree with what you did in the past, and you're trying to figure out, did I forget something or did I screw up in the past? Well, as far as I can tell, we screwed up earlier. So I think this is at least correctly analyzed the equation, but we got it wrong the last time I did this.
So if I look in the experiment, like what frequencies should I do that? Is it the cyclotron frequency?
Well, no, it's a fraction because it depends on this small parameter. So you'd have to evaluate this thing. You have to estimate what this thing is.
K parallel must be different. I mean, the flute limit should be, maybe not there, really small scale.
So when we simulated the electron MHD equation, in '94 we did this full simulation of that. And you see stuff which is very much like the PIC simulation that I just showed you is seeing. So, there's a chance that this electron MHD, and Barrett, in his simulations that he was analyzing with the electron MHD, he was seeing these little instabilities on the current layer also in the electron MHD solution. So it definitely has some similarity to what we're seeing in the PIC simulations of low beta reconnection.
One PIC simulation in which we produce tiny little vortices.
Okay, yeah.
So you're suggesting that all of this can be recovered in electron MHD. You don't need to do fixed simulation.
No, no, no. I'm not saying that. I'm saying take the electron MHD with a big grain of salt until we've proven otherwise. But you know, I think right now
There is no reason to believe that
the what?
that well, the instability exists in electron MHD, right?
Yes. There's no doubt about that.
Okay. Then the
Well,
instability
the
will lead
nonlinear
to
development,
turbulence.
well, this implementation takes some time to figure out whether you can get that.
Yeah, and furthermore, then the question is, as you crank up beta, where does it shut off? Where's the actual limit where, in the guide field, is it really true that as you crank down the guide field, this thing goes away, and where does that take place? You know, I think, I don't know. Yeah, you know, I have a feeling it's the parallel streaming. I don't think it's the rho E, actually. I think it's the, you know, typically electron kinetic effects occur in the, you know, K parallel, V parallel. So I suspect it's that. If electrons are too hot, then it smears out.
But does it become a problem if you drive the electron inertia below the Gyrokinetics scale? So
If you do what?
saying if you drive the below rho E, right?
Okay, what about that limit?
Well, you lose electron. The electron inertia is no longer the dominant field quantity.
Well, I mean, it is clear that K squared rho E squared effects are going to come in, if that's what you want to say. Anyhow, well, one thing I was, when Bill was talking about his code on Monday, his Vlasov code, I thought, wow, this is probably the way to try to analyze this thing. Because it would require a huge amount of work. So if his code can produce an instability like this and get the eigenvalues, that would be a huge benefit.
What about the structure in the y direction? Is it, I mean, do you have eigen?
No, no.
Well,
So
then
that's
the-
why we're doing local theory. We have not done that. Yeah. That's pretty much it.